Okay, please, sir.
Okay. Hello, everybody. So I am going to talk about neutrino oscillations in Japan, which sounds confusing if you don't know what it is, but hopefully it will all become clear. So, as customary, I have to introduce myself. So I was born in Liverpool in the United Kingdom, and I also got a PhD in particle physics from the University of Liverpool. So this is the downtown city centre. It's on the waterfront. It's quite nice there. You might know Liverpool if you like the Beatles, or if you like soccer, a very famous football team, or maybe you like both, in which case you'll love Liverpool. Unfortunately, I don't really like soccer, so Beatles are all right though. So you might wonder, why am I in Japan then? So when I was doing my PhD, I was working on an experiment which was called T2K. And this experiment is in Ibaraki-ken, which you may know. So I studied neutrino oscillation for my PhD topic. And actually, I first came to Japan in 2010 for my first collaboration meeting with the T2K experiment. And I liked it so much that in 2012, I moved to Tokai, which is the town where the experiment is, where the lab is. I moved there and I stayed for 2 years during my PhD. Then I went back to the UK to finish my PhD. And then I liked Japan so much, I decided to come back again. So at that time, I did a postdoc at IPMU and University of Tokyo in the Kashiwa campus. And at that time, I worked on SuperKamiokande. And I did a postdoc for 2 years, and during that time, I became very interested in deep learning. So much so that I applied to PFN and joined in January of this year. Okay, so that's me. On with the talk. So just outline what I'll talk about. So first, I'll talk about what are neutrinos, talk about why are they interesting, aka why did I dedicate 6 years of my life to them. Then I'll introduce the SuperKamiokande experiments, which is what I worked on for my postdoc. I think that's the most famous one of the two experiments. And then I'll talk about the T2K experiment too. This is kind of in reverse chronological order, but I think it makes more sense this way. So this is kind of, I think every neutrino physicist has this slide in the talks. So a neutrino is kind of, I guess, considered like a ghost particle. So neutrinos are absolutely everywhere in the universe. In fact, so much so that there are 65 billion neutrinos from the sun passing through 1 centimeter squared every second. So that's your thumbnail, 65 billion neutrinos every second going through. And like I say, they're so small, they're actually the smallest particle besides light, which is actually has no mass. So technically neutrinos are the smallest. They're so small that they pass through pretty much everything with a very, very tiny probability of actually hitting an atom or something. So basically what this means is that the mean free path of a neutrino, which means the average distance it will travel before it hits something. So the mean free path of a neutrino in lead is actually more than 1 light year. So to put that into perspective, a light year up here is 9 times 10 to the 15 meters. So if you had a block of lead that was that big, a neutrino could pass, just about pass all the way through without touching anything, which is pretty incredible. So you can see a lot of neutrinos actually are made in the center of the sun. And actually, light from the center of the sun takes 20,000 years to actually leave the sun because it keeps scattering around and hitting everything. But a neutrino will just go straight out. So this might give you some kind of insight as to why they're quite interesting. So in particle physics, we have something called the standard model, which has been developed over the last century, and it's been highly successful in explaining fundamental physics of our universe. So kind of break it down a little bit. So everything that you're made of, these three. So atoms are made from, so the nucleus of an atom is made up of these guys, and then electrons that spin around it here. But actually there's a lot more than just those. It's just that, so they have what are called generations or flavors. So you have an electron, but there's also kind of its heavier big brother called a muon, and then tau, which is very, very heavy. And generally, these things are quite unstable. They get made in high energy collisions, but eventually they will decay back down to stable things. And then over on this side, you may have heard of the Higgs boson, which is related to giving things mass. And then these things are called bosons, and they're related to the fundamental forces. So a photon mediates the electromagnetic force, and pretty much when you touch something, that's the electromagnetic force. So you never actually touch anything. The atoms of this and my finger are actually exchanging photons, and that's what's happening. You never touch the atoms. I think that's quite interesting. And then at the bottom, you have these neutrinos. So you have, so the electron has like a counterpart electron flavor of neutrino. I say flavor, they don't actually taste of anything. It's just, I guess you could say category. And then muon, mu neutrino, and tau neutrino. So out of all these particles, the neutrinos are the least understood. And in fact, in the standard model, everyone thought they didn't have any mass. Another reason why the study of neutrinos is interesting is because of something called the matter-antimatter asymmetry of the universe. So you might have noticed, but the universe is mainly matter, which is good because when matter and antimatter meet, they actually annihilate and destroy each other and create energy. So that would be pretty terrible if you met your antimatter self. So at the time of the Big Bang, there were actually equal parts matter and antimatter, but somehow all the antimatter disappeared, and we don't know why. But it's a good thing, otherwise we wouldn't exist. And something called charge parity violation in neutrinos may help to explain what happened. So basically, charge and parity are some operators which define whether something is antimatter or matter in quantum mechanics. So basically, it's violation studying of how matter and antimatter behave differently on fundamental levels. So that's another reason why you might find neutrinos interesting. So if they're so small and undetectable, then why do we even think of them? So in the 1930s, a theoretical physicist called Wolfgang Pauli, where's Tobias? Did I say that right? Yeah, good enough. He was trying to understand this process down here called beta decay, which is where, so imagine that this is the nucleus of your atom, and then in the nucleus, a neutron, with some probability, will decide it wants to become a proton, and it will kick out an electron. And yeah, so when it emits an electron, and you can measure the energy of these electrons as they get spit out. So the theoreticians were trying to calculate the theory behind this, and they observed that the measured energy spectra of the electrons that were being kicked out didn't match up with the theory. There was some missing energy. So essentially, they predicted there should have been a higher amount of energy in the spectra, but they saw a deficit. So there was some energy going somewhere, and a lot of people were seriously reconsidering whether there is such a thing as energy conservation in the universe. But luckily, there still is. So instead of breaking the fundamental law of energy conservation, Pauli decided that he would invent a massless and neutral invisible particle that would carry away some of the momentum in this equation. And he didn't really like this idea. He didn't want it to be taken too seriously, but he thought it could be a placeholder, like a temporary solution to continue the theory. And this is a nice quote from him: "I've done something very bad today by proposing a particle that can't be detected. It's something no theorist should ever do." So eventually, people figured out ways to actually measure such a particle. So in the 1950s, finally it was observed experimentally. And actually, in the true American style, the physicists in the US decided that they wanted to detonate an atomic bomb to produce a large amount of neutrinos. But eventually they came to their senses and decided that they could just use a nuclear reactor instead, because nuclear reactors put out a constant flux of neutrinos. So in theory, you could do the same measurement. So they used a 1 ton size detector to observe what's called inverse beta decay, where in this little equation here, a neutrino from the reactor will be absorbed into a proton, and then that will convert into an electron and a neutron. So what you do there is you put a big tank here, and you just sit and you wait to see an electron, and you count how many you see. So these two guys here, Cohen and Raines, they won the Nobel Prize in 1995 for this discovery. So now we know that they exist. So how do we know there's three? I like this plot because it's very, I think it's quite beautiful. Essentially, at CERN, they simulated some. So this is a decay channel of a particle in the colliders at CERN, and they calculated what's the distribution that they should see for different hypotheses. So in the 4 neutrino model, you should see this. In the 3 neutrino model, you should see this. And there's 2 neutrinos, you should see this. And they collected data from 4 different experiments and combined it together. And as you can see, the data overwhelmingly supports the 3 neutrino hypothesis. And I should point out that the error bars here are actually increased by a factor 10, so this should actually be a factor 10 smaller. And you can't see the error bars there, so I think this is very nice experimental evidence. So now we know there's 3. But unfortunately, neutrinos have a tendency to break the standard model that I introduced earlier. In contrast to the recent Higgs boson discovery, which was actually not unexpected, and in fact it actually just confirmed the theory. So there was nothing too exciting about the Higgs, rather than people saying, we were right all along. But neutrinos actually don't quite fit so well into this theory. So it was discovered that neutrinos actually aren't massless. They do have mass, which wasn't accounted for in the current theory, and they needed to make some adjustments to make it fit. Also, I think this is the most important, that neutrinos violate flavor conservation. So if you remember, I introduced these 3 flavors: electron, muon, and tau, the 3 generations. The theory says that this is like a quantity that should be conserved itself, like this. The label of the particle should be conserved. But unfortunately, neutrinos have a tendency to violate this rule, and that's essentially what neutrino oscillation is. So instead of thinking of the 3 neutrinos as 3 separate particles, actually you can think of them as a superposition of 3 eigenstates. So you have 3 definite masses, and they're actually superposition of the flavor eigenstates. So to kind of visualize this, at the top you have these 3 rows, which are the 3 mass eigenstates, but they exist as a mixture of the, so say this is the electron flavor and the muon flavor and the tau flavor. So they actually have this quantum mechanical superposition of these 3 flavor states. And the relationship between the mass and the flavor eigenstates is defined by this P, M, and S matrix. You might notice there's a lot of Japanese names here, and it was these three guys. They won a Nobel Prize as well. So essentially what this boils down to is a 3D rotation matrix with a complex phase here. And we can ignore these ones. So that defines the state, but to model the time evolution of these states, we can model the propagation as a plane wave. So this first equation here, you basically have your state times 0, and then the exponential is the plane wave solution, which depends on energy and momentum. So the probability of observing, if you start out with you know that the neutrino is flavor alpha, the probability of observing it, the same particle as flavor beta, later in time is calculated this way, which I won't go through, but essentially you can refactor it so that you get these terms, which I put down at the bottom. I don't know why the character isn't showing that, but it should be a small delta. So what this says is that the probability depends on the difference between the masses of the neutrinos, the distance it travels, L, so in kilometers, and the energy of the neutrino, so these enter as a phase term. So you have the experimental parameters, so you can design your experiment in such a way that you can, so you can kind of pick the energy of the neutrino and the distance you measure it at to get sensitivity to these model parameters, which actually explain this matrix. And actually my PhD thesis was measuring some of these numbers. So to kind of visualize what's going on here, so imagine a neutrino is created over here. So some particles decay and it spits out a muon neutrino. So you know it's a muon because it has, so you know it's a muon neutrino because it has a associated muon comes with it. And then as it propagates through time, the probabilities of the two, well, in this is a two neutrino approximation to visualize it, but you can see that over time, you have this sinusoidal pattern that is the probability. So if you were to measure the same neutrino again here, you would find that it was, it reappeared as a tau neutrino. So the thing to take away from this is that because the oscillation depends on that difference in the mass, so because of this term, if neutrinos had no mass, or even if they had the same mass, there wouldn't be any neutrino oscillation because this term would be 0. So the fact that we observe neutrino oscillation means that neutrinos must have a mass. So that's another fundamental thing about neutrinos. And something I like about this is that this effect that you're seeing here is a purely quantum mechanical effect, but it's usually you think of quantum mechanics as being very, very small, like 1 atom or something. You have to measure it in a lab, but actually this effect is taking place over hundreds of kilometers. So it really is a macroscopic manifestation of quantum mechanics. So it's a quantum mechanical effect that we can see in kind of our world, which I think is really cool. So moving on, so where do neutrinos actually come from? So you can actually make them in a particle accelerator. Actually, also, there's a lot of them that come from the upper atmosphere. So you have cosmic rays. So you have lots of stuff in space, and when they hit the upper atmosphere, they hit the oxygen molecules, and they create these showers of particles, and some of those are neutrinos. So the atmosphere is producing a lot of neutrinos. Also, a lot of neutrinos come from the sun because it has essentially a radioactive core. And also, nuclear reactors produce a lot of neutrinos. You can see in this plot, this is a real image. This isn't some computer graphic. What is happening there is the water is glowing. I'll talk about what's going on there because it's important for the detectors. Also, supernovas, when they explode. So a supernova is when a very old star collapses and then explodes. So when that happens, they emit a lot of neutrinos. And then finally, there are what they call relic neutrinos from the Big Bang that are still around. So neutrinos are everywhere in your thumb. So this glowing light of this reactor is something called Cherenkov radiation. So what happens is that, better way to introduce this is, so I introduced that experiment earlier where they were counting electrons. So essentially, you can only count a single number. It doesn't give you much information, you just know a rate. So another way to study them is using what's called Cherenkov radiation, which can give you more insight into what's going on. And so essentially what will happen is a neutrino, so in the context of this nuclear reactor here, it's this core surrounded by, in this water bath. So this, the radioactive core is spitting out lots of charged particles and neutrinos. So the neutrinos will travel into the water, and because there's so many of them being spit out, the probability of them hitting the water is high. So what happens is the neutrino hits, maybe you can see up here actually, the neutrino hits an atom, and then that will kind of, an interaction will take place, and that will spit out an electron. So the neutrino will be absorbed, electron will spit out in roughly the same direction as the neutrino. And as this electron leaves, it has a lot of energy, so it's traveling really fast. And in fact, it's traveling faster than the speed of light in water. So the speed of light in water is actually slower because it's denser. But this electron travels faster than that speed of light. And because it's doing that, it emits what's called Cherenkov radiation in this kind of cone shape. And this is basically this exact same thing that's happening in a sonic boom. So this jet here is traveling faster than the speed of sound in the air, which creates this pressure wave. So it's the exact same process, only with light. So using this light, we can infer information about the neutrino. So you have all this light, so you want to actually detect the light. So what's commonly used are photomultiplier tubes. So these are made by Hamamatsu, which I think some people in our company know about. Or I should say that they kind of are the world leaders in making these things. So essentially what it does is converts light into an amplified electric signal. So the ones used in SuperKamiokande are actually 20 inches, and they're all handmade. So it took a long time. You can actually look up this video on YouTube. It's very, very interesting. It goes through the whole construction, but I just took this screenshot of this guy glass blowing, and they did that 11,000 times. So what is actually happening inside this thing? It's a vacuum inside. So this front is coated with what's called a photocathode, and the photon will hit that, and then because there's an electric field across from the front to the back, the electron that gets kicked out of this photocathode will be accelerated towards these what are called dinodes, and then that electron will hit the dynode, and because it has this staged electric field across it, that will kick out another electron, and then the two electrons will rush to the next dynode, that kick out more electrons, and so on. So the signal is amplified through these stages, and then it eventually gets so big you can actually read it out with normal electronics. So this is a way of converting very, very weak light signals into measurable electric signals. So that brings us to the SuperKamiokande detector, which is a a very big detector in Japan. And it's essentially what I just described. It's a big tank of water with lots of these PMTs, photomultiplier tubes, on the walls and on the ceiling, all pointing inwards. So this is actually inside a mountain. So you drive into the mountain, and it's 1 kilometer underneath the peak. So the construction of this began in the very early 90s, and it finished and began taking data in 96. And I think the construction cost around 100 million in 90s money. But the cool thing about this is that it's still running today. So the amount of water in there is 50 kilotons, and it's ultra pure water, and I'll explain that in a little while. And like I say, there's around 12,000 of these photosensors on the wall. And it's actually, this cabin is big enough to fit the Statue of Liberty inside, to give you some perspective on how big it is. And this laboratory has given 2 Nobel Prizes related to experimental physics. So this guy, Koshibasa, and you might have heard of Pejita-san, who won the prize, I think, was it 2 or 3 years ago? So you might wonder, where is this thing? It's over here technically it's in Gifu Prefecture, but it's right on the border between Toyama and Gifu. So to get there, you take the Shinkansen to Toyama and then drive into the mountains. So this is what it looks like on the inside. Actually, I say it's partially filled because usually it's full to the top and there's no people in it. So this is a view when it's empty from the bottom. Someone's taken a picture, and the only real way to access it is by this kind of window washing crane from the top. So yeah, I've never actually been inside because it's been closed for 10 years. But apparently they're opening it next year for maintenance, so hopefully I'll be able to visit. So you can see here these unfortunate graduate students in this boat, and they have to take it in turns to go around and polish every single one. So this is what it's like to be a grad student in Japan. Yeah, so they basically start with no water, and they slowly raise their water level as they go around cleaning it. So yeah, it looks pretty cool. So this town where this is a place called Nozomi, and it's I took this picture. It's a very nice picture on a bridge. So the detector is actually inside this mountain back on the left. It's underneath that mountain. So this town called Nozomi, I think it has around 70 people living there. This is the bus stop where you get the bus back to Toyama. And it's about as remote in Japan as you can get, in my experience. The closest convenience store is 20 minutes drive away. That's doesn't sound like a lot if you're from the States, but in Japan, that's a big deal, I think. This is another picture I took when I was on a little walk around here. This is Kamoshika, which is a Japanese goat, dog, sheep, something. Not quite sure what it is, but they're interesting. But not pictures. Pictured here are bears, monkeys, and snakes. So when you first go here, you get the safety lecture, and it's like, wear a bear bell, stay away from the monkeys, and watch out for snakes. So yeah, it's quite fun going there. So to actually get into the mine where the detector is. So the mine is actually, it's quite an old mine. I don't think it operates fully anymore. They do a little bit of mining, but mainly now it's been converted into this research lab. It was originally a heavy metal and zinc mine. So what you do, when you think of a mine, you think you go deep underground, but actually you just drive into this tunnel. And funnily enough, it's wide open. Like, if you know where it is, you can go there. You can just get straight in. I thought there would be gates and security guards, but apparently not. So yeah, you drive in this 1 kilometer tunnel in the dark. It's pretty cool. So you drive, this road is this one. I think the actual entrance is like way over here or something. But you drive in and then you, depending on where you work, so I obviously work here. So when you go in, so the detector's running all the time, so there has to be someone, at least one person monitoring it all the time. So you have to do shifts. So there's 3 shifts per day, and I've done each one. So there's the morning shift, the afternoon shift, and then the night shift. And I think the night shift is more fun because it's very quiet, and you're in the mountains, and it's pretty cool. But only the morning shift you actually have to go into the mine. The other 2 shifts take place in the research building outside. But yeah, I basically spent my first shift, because I had to do training shifts as well as the shift block. I spent 10 days going in and out of this mine, which got a little bit frustrating after 10 days, I admit. So you might ask, why is it so deep underground? Because mining is very expensive. Why would you spend most of the budget digging a big hole? And the answer is because I mentioned before that there's constantly cosmic rays bombarding the Earth. And these, unfortunately, contribute a lot of background to the detector. So the deeper you go underground, the more these cosmic rays will be stopped by the rock. So you can kind of see this depth here. I don't know what these units are because this is an old plot. But this is essentially the rate of these particles, and they're kind of just a mix of protons and muons and neutrinos and everything. So if you're at 0, you can see the rate is off the plot. But yeah, SuperKamiokande is here. So you can see the rate is much, much lower. So the rate of SuperKamiokande now is between 1 and 10 hertz. And the rate of atmospheric neutrinos that you see in the detector is roughly 1 to 4 per day. So you can see why reducing the backgrounds is so important. So another question you might have is, why does the water need to be ultra pure? And the answer to that is because anything other than H2O, which is what water is, but water naturally has, because H2O is a solvent, so it naturally has minerals and bacteria and all kinds of stuff in the water. And anything other than H2O will attenuate the photons, so they will stop or scatter the photons and basically kind of decrease the signal inside the detector. So you really want to get rid of that stuff. Also, there's a lot of radon gas in mines, and you don't want that in the detector because radon is radioactive, so it emits radiation, which looks like neutrinos. So you want to get rid of that as well. So the way they do that is they filter it constantly, and this is quite a big system to filter 50 kilotons of water, and I can't remember the recycle rate, but it's pretty impressive. So I mentioned mean free path earlier, which is the average distance that something will travel before hitting something. So the mean free path of a photon in this tank is 70 meters. So the photon will travel 70 meters before being stopped or scattered by something. Unfortunately, that's roughly this distance, so it's the perfect value for this detector. And also, ultra pure water is very bad for you. Don't drink it, because it will suck out all of the oils and nutrients out of your body. If you drink it, you might die. If you go swimming in it, you will come out very, very itchy because it will take all the oils out of your skin. So yeah, it's not a health product at all. So just to kind of give a brief overview now of what is going on here. So this is the tank. You can see the little people on top of it. So essentially what you're doing is you're sitting and you're waiting for something to appear inside. So if a neutrino is created in the atmosphere here, it will travel through the Earth, and it will create this ring in the detector that goes upwards, so you know that something came from underneath. And because it only appeared in the detector, you know that it must have been a neutrino because nothing else can travel through the Earth. And then likewise, you get them coming down a lot more. So this is what the signal looks like. So this is, you can kind of imagine, this is kind of a top-down view inside the giant cylinder. So here you can see the neutrinos come in, and it has interacted and spat out a muon. And this muon has created this ring through the Cherenkov radiation. And you know it stopped inside because if it traveled all the way through, it would fill in this ring, so you'd get a filled-in circle. So you know pretty much where it stopped. And then another example here is neutrinos come in, interacted, but then something else has happened and it's made more stuff. So there's quite a lot of interesting topologies you can get in there. If you're interested, there is a real-time event display as well, where you can see images like this. So you can get these rings, but you can also tell what it was, because essentially, so if a mu neutrino comes in, creates a muon. The muon is what's called a minimum ionizing particle, and it just creates an electric disturbance as it travels through. But it doesn't really scatter around. But electrons, because there's electrons in the water, an electron traveling through will scatter around and create a mess. So that's what's happening here. And when it does that, it just creates this fuzzy ring pattern. But in contrast, a muon will create a very sharp ring. So there is a pattern here that you can use to discriminate between these two types. And at the moment, they use a likelihood ratio to discriminate. So they have this likelihood criteria down here, and it's based off a Monte Carlo simulation. So if it's a negative number, it's more likely to be an electron. If it's a positive number, it's more likely to be a muon. So the discovery of neutrino oscillation is basically because they predicted how many neutrinos they should see in this detector, and actually what they measured was far less. And so Kajita Sensei is the guy who won the Nobel Prize for this discovery. To quote him, the result was strange. The number of neutrinos was much fewer than expected. At first, I thought I'd made some serious mistake. And then after a year of studies, they concluded that they couldn't explain this deficit as a big problem in the data analysis or the simulation. So they ruled out this. And then in the paper that they released from this, the conclusion was that they can't explain the data as a result of an error. So some yet unaccounted for physics, such as neutrino oscillations, might explain the data. So this is the how they measured this. So this plot is called Zenith Angle. So what Zenith Angle is the angle between the North Pole and the direction the neutrino came in. So the angle that it made. So this R and R vector in between that. So the angle is very big. That means it's something coming up through the Earth. If it's very small, it's coming down. So essentially what this means is that this side of the plot, the neutrino traveled through the Earth. This side, it came straight down. So the distance the neutrino traveled is different. So the data are these points. The predicted number of neutrinos without any neutrino oscillation are these bars, and then the predicted distribution accounting for neutrino oscillation is the red curve. So you can see that if you introduce neutrino oscillations, the data and the prediction agree very, very well. So another interesting thing that SuperKamiokande can do. So in 1987, there was a supernova explosion, and it released 99% of its energy as neutrinos. And the calculations say that 10 to the 58 neutrinos were emitted, and we saw 25 on Earth. But like I said in the first slide, where the neutrino will come straight out, whereas the light will take a long time to actually leave, a neutrino essentially lets us see straight into the core of the explosion. And the neutrinos arrive before the light does. So you can have an early warning system. So if a neutrino detector sees a spike, they can send a message to astrophysicists saying, point your telescopes at this area in the sky because you're going to see a supernova explosion. So this is pretty big now in the astrophysics community. And in fact, Super-K was upgraded. The electronics were upgraded to have a very special trigger to be able to detect this kind of signal very quickly and to send out warnings. And essentially there's a supernova explosion visible on Earth roughly every 30 to 50 years in the Milky Way. And the last one was in the 80s, so we're overdue, or it should be coming soon. So SK is very anxious. And like I said, they actually want to shut down next year for maintenance. So if the supernova comes when they're shut down, they will miss their chance, and everyone will be very upset because they've dedicated a lot of their life towards this. So yeah, keeping detector uptime is very important for them.
How long in the hours you can detect the supernova?
How long? Oh, it's hours.
Hours?
Yeah, I think. I'll double check that. Okay, so 15 minutes left. So when I first came to Japan, I actually didn't work directly on SuperKamiokande. I worked on Tokai to Kamiokande, which Tokai is here in Ibaraki. So this is it's actually the site of the very first nuclear power plant in Japan, but they have this particle accelerator there as well. So the idea behind this is that you create a man-made source of neutrinos, and you fire this beam of neutrinos across Japan, underneath, essentially underground, fire it at SuperKamiokande. So why you do this is because when you create the beam of neutrinos yourself, you know very accurately the energy and the distance it travels, so you can essentially reduce the uncertainty on the parameters. So if you remember this equation here, depends on distance and energy. So if you narrow the uncertainty on these, you get a lot of precision to the actual physics parameters you want to know. And if you make a very intense beam, the probability of a neutrino hitting something increases linearly with the energy of the neutrino. So if you can make them high energy, you'll increase the probability of seeing them as well. So the collaboration is roughly 300 people from more than 10 countries. It changes all the time because people come and go. So this is a fairly recent picture. Here is Kajita Sensei, and there's me at the back. So how do you make a neutrino? Like I say, there's this particle accelerator, which is essentially just accelerating protons in this beam, like at CERN, the LHC, pretty much the same thing. So a very intense beam of protons is fired onto a target, which is made of graphite. And when you do this, it makes this huge mess of particles. And then you have these magnetic horns, which are basically just giant water-cooled magnets that focus these particles. Because they're charged, you can focus them with a magnetic field, focus them to go forwards, and then you spit them into this huge decay volume, which is 100 meters or so. You can see the picture of it there. It's filled with helium. So these particles travel through, and then they decay in flight. So the particles are unstable, so they decay, and they decay into neutrinos. And the neutrinos were created with this forward momentum, and they just keep going. So that's how you create a beam. And then you have this near detector complex here to measure the beam before it has a chance to actually oscillate its neutrinos. So this near detector complex, so this is actually how I got involved in neutrinos, because I actually built this bit inside. So it has a bunch of things. I won't go into too much detail, but this is a giant magnet. to bend the particles so you can measure their momentum. So, so what the idea behind this is that you can characterize the neutrino beam before the beam changes at all, and this lets you reduce the uncertainty in the experiment results when you measure them at SuperK. You can also make some interesting cross-section measurements. So it contains two key technologies. One of them is scintillator bars, which are these coarse things, and then it's cool name time projection chambers, which are these things to get the detailed tracking. And these are bending because they're in a magnetic field. So the scintillator modules. So actually, this is a picture of that I took from the lab when I was building this thing. So it's basically these bars that are kind of arranged in this 3D grid. Each bar has an optical fiber inside, and each fiber has an MPPC photosensor, which there's 22,000, and they all had to be put on manually. So if anyone says, do you want to build a particle physics detector, you say no, because it takes a long time. So the idea is that these fibers will absorb the scintillation light and then re-emit it in visible spectrum where the sensor can see it. So this grid lets you kind of construct tracks. So the photosensor is what's called a multi-pixel photon counter. They essentially just kind of like a small CCD, I guess. It's a grid of pixels, and then each pixel is made up of this silicon negative and positively doped parts, and then you apply a bias voltage, and the bias voltage creates this nonlinear kind of electric field across. So when a photon comes in, it will hit something, be absorbed, create an electron and an electron hole. And then this will drift this way, and then when it reaches this field, it will be amplified. So essentially you have these pixels that are able to see single photons. And when you integrate over the whole grid, you get this kind of signal. So this is the dark noise, but this peak here is the result of one pixel being hit, and then two pixels. So basically you can count multiple pixels, and if you integrate this whole signal, you get the energy that was deposited. So the other thing is this time projection chamber, this thing that you can see the fine tracks. This works by having this chamber, it's filled with argon gas. So when something comes in, so some charged particle comes in, it causes the argon, which is, so argon molecules are noble gases, so they go around in pairs, but this actually splits them up into charged particles, and then these charges will rush down and be accelerated. So you can track the charge very finely if you have these pads down here. So that's what produced these very nice curves. You can also do some discrimination between the energy because different particles will deposit different amounts of energy per unit length. So just to kind of quickly talk about how you actually get physics out of all of this, you basically simulate your predictions for both detectors, and then you reweight these simulations based on the oscillation calculations and your uncertainty studies. So you model how that affects your simulation. You perform a lot of studies of how wrong your simulations are, and then you put all of this into a likelihood function. So these are all your uncertainty terms. This is your actual PDF. So there's a few ways to deal with this likelihood. You could do a profile likelihood and use gradient descent, but I like to use MCMC. So for my thesis, I actually did a Bayesian analysis of this. And these are the results from my thesis. So this dotted line is the prediction SuperKamiokande if there were no oscillations. And then this was the data, and then this is the best fit. So you can see that you can very clearly see that oscillations exist. And then here, if you take the ratio of the two, you can see the nice dip, they call it. So the parameters, if you put them in sensitivity curves, So this blue one is the current best super K measurement using atmospheric neutrinos, and then this black curve is our measurement from the man-made neutrino beam. And you can see this was, I think, this was a few years ago, so there'll be a lot more data now. But you can see that we're already very sensitive to these parameters, and there's some other parameters too that are interesting. So now we've gone from the discovery. The T2K experiment was kind of the second generation. So the next step is to go bigger. So they had originally there was Kamiokande, then they made SuperKamiokande. So obviously the next one should be HyperKamiokande. So now there's a lot of studies and grant applications which sometimes don't succeed very well because they're asking for a lot of money to the Japanese government. So, so actually, where am I? I'm there. This was I was working on this a little bit. Basically, the idea is just build another SuperKamiokande, but make it 10 times bigger. That's it. Because you just want more data, essentially. We're still data limited. Another one, so another one of this idea of making a neutrino beam. This is the Deep Underground Neutrino Experiment, or DUNE. So this is in the US. So this is, they have an accelerator in Fermilab, which is in the outskirts of Chicago. It's quite a famous lab in the US. They want to make one of these neutrino beam experiments, but it will go all the way to South Dakota, which is around 1,300 kilometers. So basically their idea is just do everything bigger. And they actually want to use what's called liquid argon detectors, which are really cool because they have this very, very fine-grained detail. So you can really start to see all the individual. So this is an electron, and it's doing all this kind of crazy scattering. And another nice German word called Bremsstrahlung, which is braking radiation, I think. I'll get Tobias-san to say it properly later. But the point is you can really start to see all the very fine detail in what's going on here. The problem is that this is very hard to scale up, so there's a lot of studies on how to do that now. Thanks for listening.
So first of all, thanks for the very so I have multiple questions.
Yeah, sure.
So about neutrino oscillation. So the whole idea is that the neutrino and its in superposition with three eigenstates, right?
Yeah.
So it comes with an electron muon or down, right?
Yep.
And the idea is that somehow it changes. Is it known how that actually happens? Like why? Does it swap an electron or does the electron transport?
So it's more like the states were always there. It's the probability of it being one of them at any given time is the thing that's changing. So it's kind of purely quantum mechanical. So asking why it happens, like no one really knows, but they try and model it, and so far we have this mixing matrix.
But you also mentioned that the electron muon and tau have different masses. Right?
Yeah.
So if I recall my last physics correctly, I remember that some gain mass you actually need energy or introduce by energy.
Yeah, mass is essentially the same as energy. Yeah.
So how does that actually happen? I mean, where does this energy come from?
Oh, to change. So the mass. So the in the neutrinos, they're not actually changing their masses. So if you were to be able to measure a neutrino, you would kind of collapse its waveform, so you would know it. So you'd measure its mass specifically, but then you wouldn't be able to measure the flavor of it. So it's kind of this Heisenberg uncertainty principle kind of thing, where you can know one but not the other. But the mass itself is not changing. It's kind of like the interaction between you and it that's changing.
So since they're everywhere, it's also known that they actually have
no effect. They don't really do anything to you. If you were to stand in at the neutrino beam, if you were to stand there for a very long time, maybe one of them would hit you, but you're constantly being bombarded by radiation from everywhere anyway, so it's really not doing you any harm, so to speak.
Yeah. So, question. So, how did you jump from
Good question.
Yeah, I understand that you can use machine learning to analyze the experiment.
Yeah. So at first I didn't know what machine learning was, but then when I read about it, I realized that it's there's a big overlap with all of the statistics and things that I was using as a physicist. And actually we used neural networks a lot for various things in particle physics. So I had a lot of familiarity with that kind of thing. And as I did more and more data analysis, I started becoming more and more interested in learning more about the state of the art. And then eventually I realized I care more about that than neutrinos. So I decided that I should probably change my job.
So does it mean neural network or some of the machine learning techniques already used in the theoretical physics domain?
I don't know about theoretical, but in experimental certainly, because it's all manipulating data, especially at places like CERN, where they have a lot of data. So neutrino physicists don't have enough data, but at places like the LHC, they have too much data. So they really need the state of the art to handle it. And actually, up until fairly recently, it was high energy physics that was driving the big data developments. But then things like Facebook came along and started to collect more data. So now Facebook and co are the drivers. Hito-san, did you?
So the system is very complex, many parts and components. So how do you make sure that everything runs correctly without any artifacts or from parts not to get artifacts?
Right. Yeah. Lots and lots of what they call systematic uncertainty studies. So you basically have to study everything. So when you calibrate the energy from the detectors, you have to then go away and so along with the detector, they also have lots of calibration devices. So they actually have their own kind of actually they use some lasers as well to shine into the tank. But essentially you collect other data sets which are essentially labeled. So you make your own labeled data sets using lasers or small accelerators where you know the energy of whatever, and you use those data sets to study the simulation and how wrong it can be and where it can go wrong, and then you kind of capture that uncertainty and use it in measurement. So there's calibration studies and that kind of thing, but then there's also obviously lots and lots of studies by everyone for every single part to make it fit together. Along the way there'll be, but they get ironed out. Anyone else?
So no anomaly picture level.
Oh, I don't think anything general purpose, no. But just lots of error analysis, essentially. Okay, looks like everyone understood perfectly. Yeah, if you have any questions, let me know. I'll be happy to talk about it.
Thank you very much.
Thanks.